Lecture 12 begins. In Lecture 12, I will explain the first law of thermodynamics, specific heat, internal energy, and enthalpy. The content of Lecture 12 is limited to what is necessary to understand Lecture 13. The specific heat is described in Lecture 4. In Lecture 12, the specific heat is explained more in detail. If you are familiar with this subject, skip Lecture 12 and proceed to Lecture 13. In Lecture 4, the specific heat is defined as the amount of heat required to raise a 1 kilogram substance by 1 Kelvin or 1 degree of Celsius. This definition is well known. There is another definition of specific heat, that is the molar specific heat. The molar specific heat is the amount of heat required to raise 1 mole substance by 1 Kelvin. The molar specific heat will be explained after the explanation of moles. The unit of specific heat is joule over kilogram Kelvin. The unit of molar specific heat is joule over mole Kelvin. The value of specific heat depends on whether to heat at constant pressure or constant volume. In the case of gas, the specific heat at constant pressure is larger than specific heat at constant volume. For solid and liquid, such distinction is not necessary. Now, I will explain the cause of this difference. First, let's record Lecture 4. In Lecture 4, I explained that the amount of heat and amount of mechanical work are equivalent. Do you remember the technical term thermal equivalent of work? Assuming that you remember, I will move on to the explanation of the difference between Cp and Cv. To explain the heating gas, I will take 2 concrete examples. The one is to heat the gas in a container of fixed volume. The other is to heat gas in a container whose volume can be changed. The amount of heat required to raise the gas to the same temperature differs in the 2 cases. When the gas gets hot, the pressure rises and gas tries to expand. Expansion means the gas does work to the outside. In other words, a part of supplied heat is consumed for the work to the outside. If the gas does not expand, the amount of supplied heat will not be used for the work to the outside. Therefore, the gas can be heated efficiently. This is the reason why the specific heat at constant pressure Cp is larger than the specific heat at constant volume Cv. In Lecture 12, the technical terms such as internal energy and enthalpy appeared frequently. The specific heat Cp is given as the derivative of the enthalpy with respect to temperature at constant pressure. The specific heat Cv is given as the derivative of internal energy with respect to temperature at constant volume. Lecture 12 will explain how these relations are derived. Next, I will explain the basics of chemistry. Most of the following content is at the high school chemistry level. I suppose that some of you may have forgotten this kind of subject, so I dare to explain it. Atoms are made up of protons, neutrons, and electrons. Atoms are assigned a number called the mass number. The mass number is the sum of the numbers of protons and neutrons. The mass of an electron is so small that it is not included in the mass number. Examples of the mass number of a few atoms are shown in this slide. Hydrogen is a little special. Hydrogen has no neutron except deuterium and consists of only one proton, so its mass number is 1. Atoms combine to form a molecule. In general, atoms do not have unique properties or functions. The smallest unit of a substance with a function is a molecule. Oxygen atom O alone has no function, but when it becomes O2, oxygen molecule has a function such as combustion. Some molecules consist of one atom. It is called a monatomic molecule. Examples are helium, neon, and argon. Molecules are assigned a number called molecular weight. Molecular weight is the sum of the mass numbers of the atoms that make up a molecule. An oxygen molecule is made up of 2 oxygen atoms with a mass number of 16. So its molecular weight is 16 times 2 equal to 32. A water molecule has 2 hydrogen atoms and 1 oxygen atom combined together. So its molecular weight is 18. In the case of a substance consisting of multiple molecules, such as air, the molecular weight is the average of the molecular weights considering the proportion of each molecule. The Avogadro's law came out in 1811. The Avogadro's law states that under the same condition of temperature and pressure, equal volumes of different gases contain an equal number of molecules. Individual atoms and molecules are extremely small. To make quantitative treatment of such small substances easy, the unit called mole was invented. For many years before 2019, 1 mole was defined by the International System of Unit as physical quantity as a system that contains as many components as the number of atoms contained in 12 grams of carbon-12. That number was 6.022 times 10 to the 23rd powers, which is called Avogadro's number. According to the Avogadro's law, the number of molecules is the same under the same conditions, regardless of the kind of molecules or atom. This number is a universal number. As a result, in 2019, 1 mole has been redefined as a quantity containing the Avogadro's number of element particles. The number has become the base for the unit, and the specific substance name like carbon-12 has disappeared. The definition has changed, but it has virtually no influence. Both mass number and molecular weight are numerical values corresponding to the mass of a substance. In general, the mass of one mole substance can be expressed by putting grams to the number of molecular weight. 1 mole oxygen molecule weight 32 grams. In this way, it has become easy to quantitatively handle molecules that are too small. From here, I will start main subject of lecture 12. First, consider the motion of the piston in the container. The cross-section of the piston is S. If the pressure in the container higher than the outside pressure, the force acting on the surface of the piston pushes the piston. The work made by the piston is defined the product of force and moving distance. When moving distance is dx, the amount of work delta W is P times S times dx. S times dx can be expressed as volume dV. The unit of work is joule. Joule can also be expressed as N Newton times length m. If the joule is expressed by basic unit, it will be kilogram meter over sec squared. Next, I will describe the relationship between gas pressure, volume, and temperature. The slide shows that the Boyle and Charles law learned in junior high school physics. According to the Boyle's law, the pressure P and the volume V of a gas are inversely proportional at constant temperature. And according to the Charles law, the volume V and the temperature T of a gas are proportional at constant pressure. Combining Boyle and Charles law, use the equation state shown in the yellow frame. The equation in the yellow frame is quantitative. To make the equation quantitative, it is transformed into the equation shown to the right side of the yellow frame. Small v is volume of gas of m kilogram. R is called gas constant. M over V is the density rho. Using rho, the equation of the state can also be represented as shown in the red line frame. The gas constant of air is 287 joule over kilogram Kelvin. A gas that follows this equation state is called ideal gas or the perfect gas. The examples of gas regarded as ideal gas are nitrogen, helium, and air under the standard condition. Real gas under the condition of very high temperature and very low pressure can be regarded as the ideal gas. Now I should say the following explanation is mainly about ideal gases. There are two ways of represent the equation state. First, I will show the equation 1, which has been shown in the previous slide. The value of gas constant R depends on the type of gas. As I said, the gas constant of the air is 287 joule over kilogram Kelvin. The equation 1 is based on kilogram. The other gas constant is based on mole. It is shown in equation 2. While the small v in equation 1 is the volume of gas of m kilogram, the large v in equation 2 is the volume of 1 mole of gas. The pressure P and the temperature T are the same in both equation 1 and equation 2, and their units are Pascal and Kelvin respectively. Large M is the mass of 1 mole gas. The dimension of large MR is joule over mole Kelvin. Large MR is represented by RO, R0. R0 is 8.3 joule over mole Kelvin, which is a constant value regardless of the type of gas. When MR is represented by RO, R0, the equation of state 2 can be written as shown in the yellow frame. It is found from this equation that if the pressure P and the temperature T are the same, the volume of 1 mole gas is the same. The number of molecules is equal to Avogadro's number. The volume of 1 mole gas molecules under the standard condition of 0 degrees Celsius and 1 atm is 22.4 liters, regardless of the type of gas. Equation 1 tends to be used in the field of engineering, and equation 2 tends to be used in the field of physics. As shown in the figure, let's consider the case where molecules are moving around in the cube with one side L and freely colliding with the wall. Let's calculate the force that the molecules act on the wall. Assume that the collision between the molecules and the wall is perfectly elastic. Collision between molecules are ignored. In the case of a perfectly elastic collision, the velocity of the molecule after the collision changes the sign, but the magnitude of velocity is the same. The force that the wall received in one collision is given by equation 1. MP is the mass of 1 molecule. The number of times a molecule of velocity Vx collide with 1 mole per second is given by equation 2. The force that the wall received from the molecule per second is given by equation 3. The force F that 1 wall received from n molecules per second is given by equation 4. Dividing F by the surface area L squared of the cube gives the pressure. Substituting the above F into this equation, the pressure can be expressed by the equation in the red frame. Since L cubed is a volume V, PV is given by the equation 5. The result of the previous slide is for one direction. Suppose that its direction is x. The result in the x direction can be applied to the y and z directions. Kinetic energy of the particle, kinetic energy of the particle of mass mp and the velocity v is half of mp times v squared. In the right side of the equation of the arrow, PV is expressed as twice the kinetic energy. If you sum the three components and average them, PV is given by equation 6. Equation 6 is shown in the equation 7 again. The part corresponding to the small e symbol of this equation represents kinetic energy of molecule, kinetic energy molecule, which is called internal energy. Since N is Avogadro's number, E is 1 mole internal energy. Unit is joule. Equation 7 is rewritten in equation 8 using the internal energy E. Equation 8 is called Bernoulli formula. Substituting the PV of the equation state explained before to equation 8, the internal energy E is given by equation 9. It is found from equation 9 that internal energy E is the absolute temperature T multiplied by a constant. That is, the kinetic energy of molecule corresponds 1-to-1 with respect to temperature T. I will explain the first law of thermodynamics. Consider the case where the fluid is gas. The first law of thermodynamics is explained as follows. Given the heat or work, the internal kinetic energy E increases. If the gas does work or supply heat to the outside, E decreases. First, consider the case shown in the figure. The frame on the left means that heat is given and inside is heated. In the opposite case, heat is taken away. Next, consider the case where the piston is pushed by the gas and moved to the right to work on the outside. Conversely, when the piston is pushed from the outside works inside. The pressure that pushes the piston is microscopically the force that is generated by the gas molecule colliding with the wall of the piston. The first law of thermodynamics can be expressed as equation 10, shown in the yellow frame. E is the internal energy of 1 mole of gas. Delta Q represents the amount of heat inflow or outflow, and delta W represents work. Delta Q is positive for inflow and negative for outflow. Needless to say, the inner pressure is always positive. If the gas does work against outside, that is, if the piston moved to the right, then dV is positive, and so delta W is positive. Conversely, when the piston moved to the left, the gas received work from the outside. In that case, dV is negative and delta W is negative. The figure on this slide is the case when the gas gives work to the outside. The kinetic energy of the internal molecules increases or decreases depending on the inflow and outflow of heat and work. However, the value of kinetic energy is a state quantity that represents a state of the fluid like pressure, temperature, and so on. The inflow and outflow of heat and work are the causes that affect internal state, but they are not the state quantities. Therefore, the letter alphabet D is prepended to E, and the Greek letter delta is prepended to Q and W to distinguish the state quantity from Q and W. Next, let's think about the specific heat. And explanation so far, we have considered the case of heating 1 mole of gas. So we will consider the molar specific heat as a specific heat. The specific heat when heating 1 kilogram of gas can be easily converted from the molar specific heat. I will explain it later. If you move the term delta Q to the left-hand side of equation 10 becomes the equation on the first line. Substituting the equation already obtained for internal energy dE and work delta W into the equation on the first line, delta Q can be expressed as equation 11. If the volume does not change, the second term on the right-hand side of equation 11 disappeared, and thus the molar specific heat delta Q over delta T at constant volume is given by equation 12. In the case of specific heat at constant pressure, the term corresponding to the second term on the right-hand side of equation 11 remains in addition to the specific heat at constant volume. Let's use the equation state to calculate this second term. When both sides of equation state are differentiated with respect to temperature T and deformed with the constant pressure, P dV over dt becomes R0. Substituting this into the above equation, the molar specific heat at constant pressure can be obtained as shown in equation 13. The internal energy E is quantitative state, but both delta Q and delta W are not. In order to express the specific heat by the derivative of the state quantity, we introduce the enthalpy HF defined in equation 14. Enthalpy HF is a state quantity because E, P, and V are state quantities. The specific heat at constant pressure can be obtained by differentiating the enthalpy with respect to temperature T and the constant P condition, and specific heat at constant volume can be obtained by differentiating the internal energy with respect to T and the constant V condition. Such an expression is shown in equation 15. First, I will show the numerical values of the molar specific heat. Since R0 is constant, these values hold regardless of the type of gas. However, these values are derived assuming an ideal gas. It should be noted that the value of real gas is different from the value of ideal gas. Next, measure the value of molar specific heat of some real gases at constant pressure as shown. As you can see, the specific heat of real gas is considerably larger than that of the real ideal gas. However, in the case of monatomic molecules such as helium, argon, the values are close to that of ideal gas. Next, I will show you how to convert the molar specific heat to the kilogram-based specific heat. The mass kilogram of a substance in 1 mole is equal to the molecular weight of the substance divided by 1,000. The molecular weight divided by 1,000 is represented by the symbol alphabet A. The kilogram-based specific heat is the molar specific heat divided by A. As an example, let's try to convert the molar specific heat Cp of nitrogen to kilogram-based specific heat. When A is calculated using the measured value 29 of the molar specific heat, A equals 0.028. So the kilogram-based specific heat is 1036. As a second example, using the molecular weight of 28.8 for air, A is calculated as 0.0288. Calculating the kilogram-based specific heat using the ideal gas molar specific heat of 20.75 gives 720.5. The measured value of the kilogram-based specific heat of air is 1006. It's quite different from the value derived from the molar specific heat, 20.75. We know from the above result that if the specific heat is required when performing thermal calculation for real gas, it is necessary to use the data in the physical characteristic table of specific heat, except for the case of monatomic molecules. This is the end of lecture 12. Thank you.